Somewhere deep inside every atom in your body lives a force so strange that even modern physics still struggles to fully understand it. A force that becomes stronger when you try to escape it. A force carried by particles that trap themselves inside their own prison. And hidden inside that prison is an invisible storm that quietly creates almost all the mass of the visible universe. Tonight, on Velorin Sleepy Space Mysteries, we are going to descend into the strange world of gluons, the particles that hold reality together. If you watched our earlier journey into black holes and the strange fate of matter near the event horizon, you may remember how the universe often hides its deepest truths behind invisible structures. Tonight's mystery takes us even deeper, not into distant galaxies, but into the center of every proton around you. Before we begin, take a quiet moment to subscribe, leave a like, turn on notifications, and join the channel membership if these slow cosmic mysteries help you relax beneath the stars. And tell me something gentle in the comments. Where are you watching from tonight? At first glance, atoms seem simple. Tiny electrons drifting around a compact nucleus. But inside that nucleus sits a puzzle that once threatened to break all of physics. Protons should violently repel each other. Every proton carries positive electric charge. According to electromagnetism, they should explode apart instantly. Yet somehow they remain bound together inside an unimaginably tiny space. Something stronger than electromagnetism is holding them in place. That force comes from quarks, and the particles binding those quarks together are called gluons. But gluons are unlike anything else in nature. Light particles ignore each other completely. Gravity carriers, if they exist, barely interact at all. Gluons are different. Gluons feel the very force they carry. They pull on themselves, twist around themselves, trap themselves, and from that endless invisible storm emerges every star, every planet, every ocean, and every living thing that has ever existed. To understand why gluons behave so differently from every other force carrier in physics, we need to leave behind the comfortable world of ordinary intuition. Because nothing about the strong force behaves the way common sense expects. Every other force in nature grows weaker as distance increases. Gravity weakens across space. Magnetism fades with separation. Even light itself spreads thinner and thinner as it travels outward through the cosmos. But the strong force refuses to follow that rule. In fact, it does the opposite. The farther apart quarks move, the stronger the force between them becomes. And this strange behavior begins with something called color charge. Now, the name itself is unfortunate, because the word color immediately makes people imagine visible colors. Red, green, blue. But quarks are not tiny colored marbles. They are not glowing objects. There is no light involved at all. The term was simply borrowed because the mathematics of the strong force required 3 different kinds of charge. And physicists noticed that combining red, green, and blue light produces white light. The analogy was convenient, so the names remained. Every quark carries one of 3 color charges: red, green, or blue. Antiquarks carry opposite versions called anti-red, anti-green, and anti-blue. And just as ordinary electric charge determines how particles respond to electromagnetism, color charge determines how particles respond to the strong force. But immediately the system becomes stranger than electromagnetism. Electric charge comes in only two forms, positive and negative. That simplicity makes electromagnetism elegant and predictable. The strong force has 3 color charges and 3 anticolors. That already creates a much richer structure. Yet the real strangeness comes from one brutal rule imposed by nature itself. No isolated color charge is allowed to exist freely. The universe absolutely forbids it. Any particle that exists independently must be color neutral. Physicists call this a color singlet state, and nature enforces this rule with astonishing violence. Inside a proton, 3 quarks combine together. 1 red, 1 green, 1 blue. Together they produce a neutral combination. White. The proton carries no net color charge overall, even though each individual quark inside it does. Neutrons work the same way. Different quark arrangement. Same color neutrality. There is another possible combination. A quark can pair with an antiquark carrying the matching anticolor. Red with anti-red. Blue with anti-blue. Green with anti-green. These pairings create particles called mesons. Again, the total color becomes neutral. This means every stable particle built from quarks hides its color internally. From the outside, the color charge disappears completely. And yet, inside those particles, the colors never remain still. The quarks are constantly exchanging gluons, and every exchange changes their colors. A red quark emits a gluon and becomes blue. A blue quark absorbs another gluon and becomes green. The identities swirl endlessly inside the proton like dancers exchanging masks in darkness. The individual colors shift continuously, but somehow the total arrangement always remains perfectly balanced. Now we arrive at the truly extraordinary feature of gluons themselves. Photons carry electromagnetism, but photons have no electric charge. A beam of light passes through another beam without interaction. One flashlight beam ignores another completely. Photons are invisible to their own force. Gluons are different. A gluon carries color charge. This changes everything. Because a gluon carries color, it feels the strong force directly. Gluons interact with other gluons. They pull on one another, twist around one another, emit additional gluons, absorb gluons, create dense storms of self-interaction unlike anything seen elsewhere in physics. The force carrier becomes trapped inside its own force. This single property creates nearly every strange behavior associated with quantum chromodynamics. The confinement of quarks, the enormous energy trapped inside protons, the bizarre strengthening of the strong force with distance. All of it emerges from gluons interacting with themselves. Imagine if light behaved this way. Imagine if photons carried electric charge. Every beam of light would distort every other beam nearby. Starlight crossing the galaxy would tangle itself into knots. Lasers would bend and twist through their own electric fields. The universe would become unrecognizable. That is essentially how the strong force behaves at the quantum level. And because gluons interact with themselves, the mathematics describing them becomes staggeringly complicated. In electromagnetism, calculations remain manageable because photons ignore one another. In the strong force, every gluon potentially interacts with every other gluon simultaneously. The equations become deeply nonlinear, chaotic, self-referential. Even today, many problems in quantum chromodynamics cannot be solved directly. Physicists often rely on gigantic supercomputers performing lattice simulations where spacetime itself is approximated as an enormous computational grid. Only then can the behavior of quarks and gluons be estimated numerically. The irony is extraordinary. The particles responsible for holding matter together are so complicated that even the species studying them struggles to fully understand their equations. And yet every atom in your body depends on their invisible labor. Every proton in your bloodstream contains a violent ocean of gluons constantly colliding and reshaping themselves. Not calmly, not statically, but in relentless motion near the speed of light. You are not built from solid particles. You are built from confined storms. If you could somehow shrink yourself down smaller than an atom and drift into the interior of a proton, what you would witness would not resemble tiny billiard balls sitting quietly in space. The inside of a proton is not orderly. It is not static. It is one of the most violent environments in the known universe. 3 quarks race through an ocean of gluons at speeds approaching the speed of light. Around them, gluons appear and disappear constantly. New gluons emerge from older gluons. Virtual quark pairs flash briefly into existence and vanish again almost immediately. Energy churns continuously through the proton like a storm trapped inside an impossibly tiny prison. And yet, from the outside, the proton appears calm and stable. This contrast between internal chaos and external stability is one of the deepest themes in modern physics. Matter looks solid only because the violence underneath is perfectly balanced. But now imagine trying to pull one quark away from the others. At first, almost nothing unusual happens. When quarks remain extremely close together, the strong force actually becomes surprisingly weak. This strange effect is called asymptotic freedom. Inside the tiny volume of the proton, quarks move almost as though they are free particles. They bounce around with remarkable independence. For decades, this behavior completely confused physicists because it seemed to contradict the idea of the strongest force in nature. How could quarks behave freely if they were bound by something stronger than electromagnetism? The answer eventually revealed something astonishing about empty space itself. In ordinary electromagnetism, the vacuum surrounding an electric charge partially hides the charge. Virtual particles emerging briefly from quantum fluctuations create a kind of screening effect. The farther away you move from an electric charge, the weaker it appears because the vacuum dampens its influence. But gluons reverse this behavior. Because gluons carry color charge themselves, the quantum vacuum amplifies the strong force instead of screening it. The farther apart quarks become, the stronger the force grows. This discovery shocked the physics community in the early 1970s. Until then, most physicists assumed all quantum forces should weaken at short distances and strengthen only modestly at larger ones. The strong force violated that expectation completely. At close range, quarks drift almost freely. At long range, they become trapped forever. Imagine standing inside a vast invisible room with no walls. You can walk easily in any direction. Nothing stops you. But the moment you try to leave the room entirely, invisible barriers suddenly emerge around you. The farther you push outward, the stronger the walls become. That is confinement. The prison only reveals itself when escape is attempted. Now let us examine exactly how that prison forms. In electromagnetism, field lines spread outward through space. If you place two electric charges near each other, the electric field expands in every direction like ripples spreading across water. Because the field spreads thinner with distance, the force weakens naturally. But gluons refuse to spread outward cleanly. Since gluons attract other gluons, the color field between two quarks becomes compressed into a narrow tube instead of dispersing broadly through space. Physicists call this structure a flux tube, or sometimes a color string. This tube behaves almost like a stretched rubber band made from pure energy. The farther apart the quarks move, the longer the tube becomes. And because the energy inside the tube grows directly with its length, separating quarks requires more and more energy continuously. Not less energy, more. This is the opposite of nearly every force humans experience in daily life. Gravity weakens with distance. Magnetism weakens with distance. But the strong force remains relentless. Imagine trying to separate two objects connected by a cable that becomes stronger every second you pull on it. No matter how hard you struggle, the resistance never fades. It only intensifies, and eventually something extraordinary happens. The energy trapped inside the stretched flux tube becomes so enormous that nature converts the energy directly into matter. A brand new quark and antiquark suddenly emerge from empty space. This is Einstein's equation unfolding in its purest form. Energy becoming mass. Not metaphorically, literally. The original flux tube snaps into two smaller tubes. The newly created antiquark attaches to the escaping quark, forming a meson. The newly created quark reconnects with the remaining quarks left behind. Instead of isolating a single quark, the universe simply creates new particles. The prison repairs itself automatically. No matter how much energy you inject into the system, no isolated quark ever appears. More energy does not produce freedom. It only produces more confined particles. This phenomenon has been tested repeatedly inside particle accelerators. Scientists smash protons together at unimaginable energies, hoping to expose their internal structure. And for brief moments, the quarks inside scatter violently apart. But within less than a trillionth of a second, confinement returns. Flux tubes form instantly. New particles emerge. Jets of hadrons spray outward through detectors. But never a lone quark. Never once. Not in any experiment ever performed. This permanence is difficult to emotionally grasp because human intuition evolved in a world where separation is always possible. We can pull objects apart, break bonds, isolate components, but the strong force denies that possibility completely. A quark has never existed alone anywhere in the modern universe. The quarks inside your body have been confined since the first moments after the Big Bang, trapped continuously for nearly 14 billion years. They were confined inside ancient stars, confined inside exploding supernovae, confined while planets formed, confined while life emerged on Earth. And they will remain confined long after humanity disappears into cosmic history. The most fundamental building blocks of matter are prisoners that can never escape their own existence. There is another mystery hidden inside the proton. A mystery so surprising that when physicists first uncovered it, many refused to believe the measurements were correct. because according to the earliest models of matter, the mass of a proton should come mostly from the masses of the three quarks inside it. That seemed obvious. After all, matter is supposed to get its mass from the particles composing it. Add the masses together and you obtain the total. Simple. Except nature ignored that expectation completely. The three quarks inside a proton contribute only a tiny fraction of the proton's actual mass. Barely more than 1%. This means almost all the mass of ordinary matter does not come from quarks themselves. It comes from gluons. Or more precisely, it comes from the energy trapped inside the gluon field. To understand how astonishing this is, consider your own body for a moment. Every muscle, every bone, every drop of blood, nearly all of your physical mass originates not from solid material particles, but from confined energy swirling inside protons and neutrons. You are made mostly from motion, mostly from tension, mostly from trapped energy held inside invisible cages created by gluons. This idea feels almost unreal because human intuition expects matter to be made from substance. Tiny solid components stacked together like grains of sand. But at the quantum level, solidity dissolves into fields, vibrations, and dynamic interactions. The proton is not a tiny hard sphere. It is a storm. Inside that storm, quarks move at enormous velocities. Gluons collide constantly. Flux tubes twist and reconnect endlessly. Virtual particle pairs emerge from the vacuum and vanish again. The entire proton behaves less like an object and more like a contained explosion frozen into stability. And all of that activity carries energy. According to relativity, energy possesses inertia. Energy contributes mass. The more energy trapped inside a system, the heavier the system becomes. The proton's mass therefore emerges primarily from the kinetic energy of quarks and the enormous binding energy stored inside the gluon field. This realization changed humanity's understanding of matter itself. For thousands of years, philosophers imagined substance as something static, something permanent. Ancient thinkers believed the world must ultimately reduce to indivisible solid pieces, tiny eternal fragments forming larger structures. But modern physics revealed something far stranger. The visible universe is not built from little solid beads. It is built from vibrating fields carrying energy through space. Even the proton, one of the most stable structures in existence, is internally turbulent beyond comprehension. And this turbulence never stops. Every second of your life, countless gluon interactions erupt inside every proton of your body. The violence is continuous. Yet because the scales involved are unimaginably small, the chaos averages into stability. There is something almost poetic about this. Calmness emerging from chaos, structure emerging from turbulence, reality itself balanced delicately atop storms too small for human senses to perceive. Now let us step deeper into the gluon field itself, because another remarkable possibility emerges from gluon self-interaction. Since gluons carry color charge, gluons can bind directly to other gluons even without quarks being present at all. This means the strong force may be capable of creating particles made entirely from pure gluon energy. These hypothetical particles are called glue balls. A glue ball would contain no quarks whatsoever, only gluons trapped together through their own self-interactions. A knot of pure force holding itself together. Physics predicts they should exist. But finding them has proven extraordinarily difficult because once created, glue balls decay rapidly into ordinary particles. Their signatures blend almost perfectly with conventional mesons. Experiments continue searching for unmistakable evidence, but identifying a true glue ball remains one of the major unresolved challenges in particle physics. Still, the possibility itself is astonishing. Particle made entirely from force, not matter carrying force. Force becoming matter directly. Again and again, the strong interaction erases the comfortable boundary humans once imagined between energy and substance. Now let us return briefly to the early universe because confinement itself was not always active in the way it is today. Immediately after the Big Bang, temperatures were so extreme that protons and neutrons could not exist. Matter had not yet condensed into stable atomic nuclei. Instead, the universe contained a dense plasma of free-moving quarks and gluons called quark-gluon plasma. For a brief cosmic moment, confinement dissolved. Quarks and gluons moved collectively through an environment hotter than the cores of modern stars by thousands of times. Temperatures reached trillions of degrees. Under such conditions, the ordinary structures of matter melted completely. But even then, quarks were not truly free in the everyday sense. They still interacted intensely with surrounding gluons. The plasma behaved almost like a perfect liquid with astonishingly low viscosity. Instead of individual particles bouncing independently, the entire medium flowed collectively as one dynamic fluid. Modern particle colliders recreate tiny droplets of this ancient state by smashing heavy atomic nuclei together near light speed. For unimaginably brief instants, miniature fireballs appear that resemble the universe microseconds after the Big Bang. Then the plasma cools. Confinement returns. And ordinary matter reassembles itself once again. In a sense, every collision inside these accelerators briefly tears open a window into the earliest chapter of cosmic history. And what physicists repeatedly observe confirms the same extraordinary truth. Confinement dominates the modern universe completely. The strong force never truly relaxes its grip. Every proton around you is therefore an ancient survivor, a stabilized remnant forged during the universe's first moments. The quarks inside it have remained trapped ever since, held together by gluons that endlessly interact with themselves in invisible storms beyond direct observation. You have never seen a gluon. You never will. No isolated gluon can survive outside confinement. And yet every atom around you depends entirely on their hidden existence. The universe is held together by particles humanity can never directly touch. One of the strangest aspects of gluons is that physicists understand them with extraordinary precision and yet still cannot fully solve the equations describing them. This tension sits at the heart of modern particle physics. Quantum chromodynamics predicts experimental results with remarkable accuracy. Particle colliders confirm its principles again and again. The existence of quarks, the existence of gluons, the behavior of jets, the confinement of color charge. All of it matches observation with stunning consistency. And yet the equations themselves become so tangled through gluon self-interaction that many of their deepest consequences remain mathematically hidden. It is almost as though nature allows humanity to glimpse the machinery of reality without fully handing over the instructions. The equations governing the strong force belong to a family called Yang-Mills theories. These theories describe fields whose force carriers interact with themselves. Unlike electromagnetism, where photons pass through one another peacefully, Yang-Mills fields generate intricate webs of self-interaction that quickly become overwhelmingly complex. Even tiny changes ripple through the equations endlessly. A gluon affects another gluon, which affects another, which feeds back into the original interaction. The system folds inward upon itself like an infinite hall of mirrors. For this reason, physicists often rely on numerical simulations instead of direct solutions. Massive supercomputers divide spacetime into tiny lattice grids and calculate how quarks and gluons evolve point by point. These simulations require enormous computational power. Some calculations take months. Others remain beyond current capabilities entirely. And despite decades of effort, one fundamental mathematical question still remains unresolved. Can confinement be rigorously proven from first principles? Physicists know confinement is real. Every experiment confirms it. Every simulation reproduces it. But a fully rigorous proof derived directly from the Yang-Mills equations has never been achieved. In fact, this problem became so important that the Clay Mathematics Institute included it among the Millennium Prize problems. A $1 million prize still waits for anyone capable of proving mathematically why the strong force necessarily produces confinement and a mass gap. The prize remains unclaimed. There is something deeply humbling about this. Human civilization has split the atom, reached the moon, built machines capable of recreating conditions from the early universe. And yet the force responsible for holding ordinary matter together still hides part of its logic behind mathematical shadows. The closer we approach the foundations of reality, the stranger reality becomes. Now let us step back for a moment and consider what confinement truly means on a cosmic scale. Everything visible around you exists because quarks cannot escape. Every mountain, every ocean, every heartbeat, every drifting cloud beneath the evening sky. All stable matter depends entirely on the permanent imprisonment of quarks inside hadrons. If confinement suddenly vanished, protons and neutrons would immediately disintegrate. Atomic nuclei would collapse. Chemistry would cease to exist. The familiar world would dissolve into an expanding plasma of unbound particles almost instantly. Stars could not burn. Planets could not form. Life could never emerge. Confinement is not merely a detail of particle physics. It is one of the deepest structural rules shaping the universe itself. And yet, the prison responsible for all matter has no physical walls. No bars, no boundaries, only self-interacting fields stretching through quantum space. This makes the strong force feel almost philosophical. Unlike gravity, which gently pulls across cosmic distances, or electromagnetism, which governs the visible interactions of daily life, the strong force operates in secrecy, hidden inside atomic nuclei, invisible to ordinary perception, silent beneath the surface of reality. And still it dominates the mass of the universe. When you hold a stone in your hand, most of its weight comes from gluon energy. When you stand beneath the night sky, the stars above are composed primarily of confined energy generated by gluon dynamics inside protons and neutrons. Even your own body is stabilized by invisible flux tubes endlessly forming and collapsing within matter. The visible world is built upon hidden confinement. There is another layer of strangeness here as well. Because although gluons create confinement, the quarks inside hadrons simultaneously experience asymptotic freedom at extremely short distances. This means quarks exist in a bizarre state between imprisonment and liberty. Deep inside the proton they move almost freely, but any attempt to separate them awakens the full violence of confinement. Freedom exists only within the prison itself. This duality gives the proton an almost paradoxical nature. The quarks inside are neither fully bound nor fully free. They occupy a constantly shifting middle state governed by energy scales and quantum fluctuations. Reality at its deepest level refuses simple categories. Particles become waves. Empty space becomes active. Force becomes matter. Motion becomes mass. Freedom becomes confinement. And perhaps that is why the gluon remains one of the most profound discoveries in modern science. Not because it is large or dramatic or directly visible, but because it reveals how strange the hidden architecture of existence truly is. Every second, trillions upon trillions of gluons interact silently throughout your body. Their fields weave together inside every atom around you. They hold ancient quarks captive with absolute permanence while simultaneously generating nearly all visible mass through pure energy. You cannot see them. You cannot isolate them. You cannot touch them directly. And yet, without them, the universe would lose its structure entirely. The stars would fade into meaningless particle clouds. Matter itself would unravel. The gluon is invisible, massless, forever confined. But it is also one of the most important entities in the cosmos. A particle that traps itself while building the material universe from imprisoned energy. And perhaps somewhere inside that strange contradiction lies a deeper truth about reality itself. That the universe is not built from stillness, not from solidity, not from permanent objects resting quietly in empty space, but from restless fields, endless motion, invisible tensions, and storms so small that only mathematics can hear them. For most of human history, people believed the visible world was solid and continuous. Stone felt permanent. Metal felt dense. Even air seemed like a smooth, invisible substance filling empty space. The deeper structure beneath matter remained hidden from ordinary perception. Only in the last century did humanity begin peeling back those layers one by one. Molecules dissolved into atoms. Atoms dissolved into nuclei and electrons. Nuclei dissolved into quarks and gluons. And at every stage, reality became less intuitive and more dreamlike. The gluon may be the clearest example of this transformation, because unlike ordinary objects, gluons cannot exist independently. They cannot be isolated and displayed like tiny marbles beneath a microscope. Their existence is inferred through patterns, equations, and the invisible traces left behind after high-energy collisions. In a strange sense, physicists study gluons the way ancient sailors studied wind. The wind itself remains unseen. Only its effects become visible. Leaves move, waves rise, clouds drift across the sky. From those movements, the invisible force is reconstructed. Gluons reveal themselves the same way. Inside giant particle accelerators, protons are smashed together at nearly the speed of light. The collisions are unimaginably violent. For brief moments, Energies become high enough that the internal quarks and gluons inside the proton scatter violently apart. Detectors surrounding the collision chamber record enormous sprays of particles erupting outward. At first glance, the patterns look chaotic. Thousands of new particles appear almost instantly. But hidden inside that apparent disorder are elegant structures called jets. A jet is essentially the fingerprint of a quark or gluon. When a high-energy quark shoots away from a collision point, confinement immediately activates. The quark cannot remain isolated. Flux tubes form around it almost instantly. New quark-antiquark pairs emerge from the vacuum. Additional hadrons form in rapid succession. The result is a narrow spray of particles all traveling roughly in the same direction. That spray becomes visible inside the detector. The original quark remains invisible, but its motion leaves behind a trail of confined descendants. Gluons produce jets as well, and because gluons interact more strongly than quarks, gluon jets often appear broader and more diffuse. Their self-interactions generate more secondary particles as they evolve. By carefully studying these jets, physicists learned how gluons behave without ever directly observing a free gluon itself. One of the great milestones came in 1979 at the Petra Accelerator in Germany. Scientists were studying collisions between electrons and positrons. Normally, such collisions produce a quark and antiquark moving in opposite directions, creating two back-to-back jets. But occasionally a third jet appeared. This third jet matched the exact predictions expected if one of the quarks had emitted a gluon before confinement restored itself. It was the first unmistakable evidence that gluons truly existed, not as abstract mathematical symbols, but as real physical entities carrying energy and momentum through the quantum world. The discovery was so important because it confirmed something profound. The strong force was not merely a mysterious attraction between quarks. It was a fully dynamic quantum field with its own independent particles, its own internal structure, and its own astonishing rules. And those rules differed radically from every other force humanity had encountered. Even today, physicists continue probing the strong force at ever higher energies, hoping to uncover deeper layers beneath quantum chromodynamics itself. Because although QCD explains the behavior of quarks and gluons extraordinarily well, many mysteries remain unresolved. For example, why do quarks possess the masses they do? Why are there exactly 6 flavors of quarks instead of 3 or 10? Why does confinement emerge so perfectly and universally? Why does the universe choose this particular symmetry structure for color charge? These questions drift at the edge of modern understanding like distant stars barely visible through fog. And perhaps the strangest mystery of all concerns simplicity itself. Because the equations of QCD are surprisingly compact. The underlying mathematical framework is not impossibly enormous. A handful of elegant principles generate all the complexity of the strong force. Yet from those relatively concise equations emerges nearly all visible mass in existence. This contrast between simple rules and overwhelming complexity appears repeatedly throughout nature. Tiny DNA molecules generate entire ecosystems. Simple gravitational equations create galaxies and black holes. Basic quantum fields give rise to chemistry, biology, and consciousness. Reality seems to possess an extraordinary ability to build infinite richness from minimal ingredients. The gluon is one of those ingredients, And yet the gluon also reveals something unsettling about reductionism. Human intuition often assumes that if we break reality into smaller and smaller pieces, we will eventually reach simple little objects sitting quietly at the bottom. But the deeper physics goes, the less object-like reality becomes. The proton is not a container filled with tiny balls. It is a constantly fluctuating field structure. Even the number of particles inside a proton changes continuously. Gluons split into quark-antiquark pairs. Those pairs annihilate back into gluons. Virtual particles emerge and vanish endlessly. At high energies, the proton behaves almost like a dense foam of quantum activity rather than a stable collection of permanent components. This means asking how many particles exist inside a proton at any moment becomes surprisingly difficult. The answer depends partly on how closely you examine it. At lower energies, a proton seems dominated by 3 valence quarks. But at higher energies, countless additional gluons and transient quark pairs become visible within the proton's internal structure. The proton therefore changes character depending on how deeply it is probed. Reality itself becomes scale-dependent. What appears simple from one perspective becomes turbulent from another. And somewhere inside that turbulence, gluons continue their invisible labor, binding quarks together, generating mass, maintaining confinement, quietly sustaining the material universe through endless interactions too small and too rapid for direct human experience. The stability of matter rests atop storms that never sleep. There is a tendency in science to imagine progress as a movement toward certainty, a gradual clearing of confusion until reality finally stands exposed in complete detail. But the deeper humanity explores the quantum world, the more nature seems to resist clean explanation. Every answer opens new mysteries. Every layer beneath matter reveals structures stranger than the last. And the gluon sits near the center of that unfolding mystery like an invisible architect hidden behind the walls of existence. Consider again the strange paradox of confinement and asymptotic freedom existing simultaneously. At large distances, quarks become prisoners held by overwhelming force. At tiny distances, they move almost freely through the interior of the proton. The same interaction produces both liberation and imprisonment depending entirely on scale. This dual behavior once seemed impossible. Yet experiments confirmed it repeatedly. When physicists fired high-energy electrons into protons during deep inelastic scattering experiments, the electrons behaved almost as though they were striking independent particles moving freely inside the proton. The quarks appeared loose, barely interacting. For a time, this result deeply confused researchers because the strong force was supposed to be overwhelmingly powerful. The contradiction remained unresolved until the mathematics of asymptotic freedom emerged. At very short distances, gluon anti-screening weakens the effective force between quarks. The quarks become nearly independent. But as separation increases, the gluon field amplifies itself and confinement rapidly takes over. The proton therefore contains a hidden transition between 2 radically different behaviors: freedom near the center, captivity at the edges. It is almost like a cosmic trap designed with extraordinary precision. And yet this strange arrangement may be exactly what allows stable matter to exist at all. If confinement operated strongly even at microscopic distances, quarks would become frozen rigidly in place. protons might lose their dynamic internal structure entirely. But if asymptotic freedom extended too far outward, quarks could escape confinement and matter would dissolve into unbound plasma. The universe appears balanced delicately between these extremes. Too much confinement would destroy flexibility. Too little confinement would destroy structure. Somehow the strong force occupies the narrow region where stability becomes possible. This balancing act echoes across many scales of nature. Stars balance gravity against fusion pressure. Galaxies balance order against chaotic motion. Biological systems balance stability against adaptation. Again and again, complexity emerges not from absolute rigidity or total freedom, but from systems poised between competing tendencies. The proton itself may be another example of that universal pattern. Now let us descend briefly into neutron stars because nowhere in the modern universe does confinement face greater pressure. A neutron star forms when a massive star exhausts its nuclear fuel and collapses inward under gravity. The outer layers explode into space as a supernova while the core compresses beyond ordinary atomic density. Matter becomes crushed so tightly that electrons merge with protons, producing an immense sphere composed mostly of neutrons. Inside a neutron star, densities become almost unimaginable. A teaspoon of neutron star material would weigh billions of tons on Earth. Under such conditions, physicists suspect confinement may begin partially breaking down deep within the core. Some theories propose that quarks inside neutrons dissolve into a dense quark matter phase where confinement weakens dramatically. Others suggest exotic forms of color superconductivity may emerge as quarks pair together in entirely new arrangements. No one yet knows the exact truth because these conditions remain far beyond direct laboratory reproduction. But neutron stars may contain the closest modern equivalent to the quark-gluon plasma of the early universe. Entire stars balanced at the threshold where confinement itself begins to strain under cosmic pressure. And even here, gluons remain central actors shaping the behavior of matter. The strong force determines the stiffness of neutron star material. It influences how large neutron stars can become before collapsing into black holes. It affects the ripples of gravitational waves produced when neutron stars collide. Invisible gluon interactions inside atomic nuclei therefore influence events occurring across entire galaxies. The smallest scales shape the largest. This connection between microscopic and cosmic structure is one of the most beautiful aspects of physics. Human intuition often separates the tiny from the immense. Atoms seem disconnected from stars. Quarks seem irrelevant to galaxies. Yet reality ties them together continuously. Without gluons, stars could not fuse elements properly because stable nuclei would not exist. Without stable nuclei, supernovae could not forge heavy atoms. Without heavy atoms, rocky planets could never form. Without planets rich in chemistry, biology would never emerge. The existence of life itself traces backward through nuclear physics into the hidden dynamics of gluons. And still the gluon remains invisible. No telescope has ever photographed one. No microscope can isolate one. Even the most advanced detectors only infer their existence indirectly through jets and scattering patterns. This creates a fascinating tension in modern science. Some of the most important entities in reality are permanently inaccessible to direct perception. Human beings evolved to trust visible things. Mountains, trees, oceans. faces illuminated by sunlight. Yet the deeper architecture of existence operates largely beyond sensory intuition. Quantum fields, curved spacetime, dark matter, gluon confinement. Reality becomes increasingly abstract as understanding deepens. And perhaps this is unavoidable. The universe was never designed around human comfort or biological intuition. Evolution shaped human perception only for survival on the African savanna, not for understanding the quantum structure of matter. Still, despite these limitations, humanity uncovered gluons through mathematics, experimentation, and imagination, an invisible particle carrying a force that traps itself. A field strong enough to imprison quarks forever while simultaneously generating nearly all visible mass. A hidden storm existing inside every atom around you at this very moment. The deeper one reflects on it, the more extraordinary ordinary matter begins to feel. There is a quiet irony hidden inside the history of physics. The stronger humanity's instruments became, the less solid reality appeared. Early scientists imagined atoms as miniature solar systems, tiny electrons orbiting compact nuclei in orderly patterns. Felt understandable, mechanical, predictable. But every improvement in experimental precision dissolved another layer of certainty. Electrons stopped behaving like particles alone and became probability waves. Empty space revealed itself as an active quantum vacuum filled with fluctuations. Time and space merged into curved spacetime under relativity. And deep inside atomic nuclei, gluons transformed matter itself into something restless and dynamic. The closer science moved toward the foundations of existence, the more the universe resembled an ongoing process rather than a collection of objects. This becomes especially clear inside the proton. When people imagine a proton, they often picture three quarks sitting inside a small sphere. But this image is deeply misleading. The proton is not three permanent particles arranged neatly in space. Most of the proton's internal activity comes from transient gluons and virtual quark pairs appearing and disappearing continuously. In fact, at high energies, gluons dominate the proton completely. As physicists probe the proton more deeply, they discover increasing numbers of low-energy gluons crowding its interior. The proton begins to resemble a dense ocean of gluon fields rather than a simple three-quark structure. This creates one of the strangest situations in all of science. The particles primarily responsible for the proton's mass are themselves massless. Gluons have zero rest mass. And yet, through their interactions, they generate nearly all the mass of ordinary matter. It feels almost impossible intuitively. How can massless particles create massive objects? But the answer lies in energy itself. The proton's mass emerges not from the individual masses of particles inside it, but from the total energy trapped within the confined system. Motion contributes mass. Binding energy contributes mass. Field energy contributes mass. A proton therefore weighs far more than the sum of its ingredients because the gluon field contains enormous energy density. And this idea extends far beyond protons. The visible universe itself may be understood less as a collection of material things and more as a vast arrangement of interacting energy fields stabilized into temporary structures. Even solidity becomes an illusion of force interactions. When your hand touches a table, atoms never truly collide. Electromagnetic forces between electron clouds create resistance long before nuclei physically meet. Matter feels solid because fields repel one another. At the deepest level, reality becomes interactions all the way down. Fields interacting with fields. Gluons interacting with gluons. Energy shaping energy. This perspective changes how one sees ordinary existence. A mountain no longer appears merely as rock. It becomes a gigantic arrangement of confined quantum fields stabilized across geological time. A human body becomes an organized flow of atomic interactions sustained through chemistry and biological structure. Even sunlight becomes a stream of quantum excitations crossing 93 million miles of space before reaching Earth. The familiar world quietly dissolves into processes. And hidden beneath all those processes, gluons remain among the most essential actors. Now let us consider another extraordinary property of the strong force. Unlike gravity or electromagnetism, the strong interaction operates only across extremely tiny distances. Beyond roughly the width of an atomic nucleus, the force falls away rapidly. This short range emerges directly from confinement. Because gluons become trapped inside hadrons, the strong force cannot spread freely across large distances the way light or gravity can. The force becomes effectively sealed inside atomic nuclei. And yet, despite its microscopic range, the strong force is so powerful that it overwhelms electromagnetism inside the nucleus completely. Remember how astonishing this truly is. Every proton carries positive electric charge. According to electromagnetism, nuclei should explode apart instantly. In heavy atoms like uranium, dozens of positively charged protons crowd together inside a minuscule space. The repulsive electric force becomes enormous. But gluons operating through residual nuclear forces still hold the nucleus together. Without that hidden confinement structure deep inside protons and neutrons, atomic matter could never remain stable. The entire periodic table therefore rests indirectly upon gluon dynamics. Hydrogen, carbon, oxygen, iron, gold, uranium. Every chemical element owes its existence to confinement. And because chemistry depends on stable nuclei, every biological process depends on confinement as well. DNA exists because confinement exists. Water exists because confinement exists. Human consciousness itself emerges from chemistry ultimately rooted in gluon fields. It is remarkable how often the deepest foundations of reality remain invisible within ordinary life. People wake each morning surrounded by stable matter without ever sensing the extraordinary mechanisms preserving it. The atoms inside a glass of water appear calm and uneventful. Yet inside every proton, quarks race through violent gluon storms beyond direct imagination. Reality contains hidden layers of motion beneath every quiet surface. There is another philosophical lesson hidden here too. Humans often divide the universe into opposites. Matter versus energy, stability versus motion, structure versus chaos. But the gluon reveals how deeply intertwined these concepts truly are. The proton remains stable precisely because of internal motion. Mass emerges because of energy. Structure survives because of turbulence balanced perfectly through confinement. Stillness itself becomes a form of organized activity. And perhaps that idea extends beyond physics. Galaxies remain stable through orbital motion. Ecosystems remain stable through countless living interactions. Even civilizations persist through continuous flows of information, labor, and adaptation. The universe rarely achieves permanence through stillness alone. Instead, stability emerges from balanced movement. The proton may be one of the smallest examples of that universal principle. A stable object formed from endless internal storms. Invisible storms, silent storms, storms carried by massless particles humanity can never isolate from the prison they create for themselves. And yet those imprisoned particles quietly hold the visible universe together every second of every day. Perhaps the most unsettling realization about gluons is that the universe depends on something humanity can never fully observe directly. Science often aims toward visibility. Telescopes reveal distant galaxies. Microscopes reveal hidden cells. Detectors reveal subatomic particles. Again and again, progress seems tied to seeing more clearly. But gluons resist that pattern. Their defining property guarantees permanent invisibility in isolation. The stronger the force becomes, the less directly observable its carriers are. This creates an unusual relationship between knowledge and evidence. Physicists know gluons exist with overwhelming confidence. Their effects appear everywhere in high-energy experiments. The equations describing them predict scattering events with astonishing precision. Jet structures inside particle collisions behave exactly as quantum chromodynamics predicts. And yet no scientist has ever held evidence of a single isolated gluon detached from confinement. The particle remains hidden behind its own laws. In some ways, this mirrors gravity itself. Humanity has never directly observed a graviton either, assuming gravitons exist at all. We observe gravity through falling objects, orbiting planets, warped space-time, and gravitational waves. The invisible becomes knowable through consequence rather than direct exposure. Modern physics, therefore, relies increasingly on indirect truth. Reality leaves fingerprints instead of portraits. And the gluon leaves fingerprints everywhere. Inside particle colliders, detectors capture immense cascades of hadrons erupting from collisions at nearly light speed. By tracing those sprays backward mathematically, physicists reconstruct the invisible interactions that occurred beforehand. A scattered quark here, a radiated gluon there, tiny exchanges of color charge hidden beneath the explosion of visible particles. It is almost archaeological. Scientists reconstruct vanished quantum events from debris patterns lasting less than a trillionth of a second. And somehow, from those fleeting traces, an entire theory of confinement emerged. But there is another mystery woven into all this. One that reaches beyond particle physics itself. Why does the universe permit mathematics to describe reality so effectively? The equations governing gluons are abstract symbols written by human minds. Group symmetries, quantum fields, nonlinear interactions across complex space-time geometries. Yet those symbols somehow predict the behavior of matter with extraordinary precision. The proton does not know mathematics consciously. Quarks do not solve equations. Gluons do not calculate confinement. And yet reality unfolds exactly according to structures human beings can encode symbolically. This strange harmony between mathematics and existence has fascinated scientists and philosophers for centuries. Some view mathematics as humanity's invention. Others suspect mathematics reflects something deeply woven into the structure of reality itself. The gluon intensifies that mystery because quantum chromodynamics becomes almost unimaginably abstract at advanced levels. The theory relies on symmetries existing in mathematical spaces completely detached from ordinary human experience. Color charge itself is not literal color. It is a property emerging from internal gauge symmetries represented mathematically through SU3 group structures. And yet, from those abstractions emerges the physical stability of every atom around you. The universe behaves as though hidden mathematical architecture underlies visible existence. There is something strangely beautiful about that. Invisible symmetries generating stars. Abstract equations generating mountains. Quantum fields generating consciousness capable of wondering about quantum fields. The universe folding back upon itself in awareness. Now let us imagine for a moment what existence would feel like inside a world without confinement. Suppose gluons behaved like photons. Suppose the strong force weakened with distance normally instead of strengthening. Quarks could drift freely through space. Protons and neutrons would never stabilize permanently. Atomic nuclei would disintegrate. Perhaps tiny temporary bound states might appear briefly, but large stable chemistry would almost certainly become impossible. Without stable nuclei, stars would struggle to sustain nuclear fusion in familiar ways. Heavy elements might never form. Carbon chemistry might never emerge. Biological evolution could fail before it ever truly began. A universe without confinement might remain forever simple. Thin clouds of drifting particles expanding through darkness without planets, oceans, or living systems. Complexity itself may depend on imprisonment. This is one of the strangest implications of the strong force. Freedom at the most fundamental level could actually prevent higher structures from forming. Stable reality requires confinement. The universe builds richness not despite restrictions, but because of them. And perhaps this idea extends far beyond physics. Music requires structure. Language requires grammar. Galaxies require gravity. Biological life requires chemical constraints. Again and again, order emerges because certain possibilities are forbidden while others remain allowed. Confinement may therefore represent one expression of a broader cosmic principle. Creativity emerging through limitation. The proton becomes stable because quarks cannot escape. Matter becomes stable because confinement never relaxes. Life becomes possible because gluons refuse to behave normally. There is something quietly profound about that realization, especially when viewed beneath the night sky. Every distant star overhead contains trillions upon trillions of confined quarks held together through invisible gluon interactions. Every atom drifting through interstellar space carries ancient confinement structures forged near the beginning of cosmic time. Even the calcium inside human bones was assembled inside stars whose nuclei depended entirely on gluon dynamics. The visible universe is therefore not merely illuminated by stars. It is constructed from confinement itself. And all of it rests upon one strange fact. The force carrier of the strong interaction carries its own charge. That single property transforms everything. It creates flux tubes instead of spreading fields. It creates asymptotic freedom at tiny scales and confinement at larger ones. It traps quarks forever while simultaneously generating nearly all visible mass through pure energy. One subtle difference in the laws of physics reshaped the entire universe. And perhaps that is the final lesson hidden inside the gluon. Reality may not require countless separate rules to create complexity. Sometimes one unusual principle is enough to transform everything that follows. A single self-interacting particle, an invisible prison, and from that prison emerged stars, planets, oceans, and living minds capable of slowly uncovering the strange hidden storms buried inside matter itself. There is a moment late at night when the universe begins to feel less like a place and more like a process. The stars no longer seem fixed. The ground beneath your feet no longer feels perfectly solid. Everything begins to soften into motion, into patterns, into flows of invisible energy unfolding quietly beneath the surface of ordinary life. The gluon belongs to that hidden layer of reality. It is not a particle anyone will ever hold in their hand. It does not drift freely through space like light. It cannot travel across the cosmos independently the way photons do. The gluon exists almost entirely inside confinement, buried within protons and neutrons, trapped inside the structures it helps create. And yet, despite that invisibility, its influence reaches everywhere. Every heartbeat inside your chest depends on stable atomic nuclei held together ultimately through gluon dynamics. Every memory formed inside your brain depends on chemical reactions rooted in atoms whose protons remain stable only because confinement never fails. The warmth of sunlight touching your skin began inside stellar cores where nuclear processes relied completely on the strong interaction. The gluon hides beneath existence like an unseen foundation stone beneath an ancient city. Most people move through life never realizing such particles exist. They see tables, trees, rain falling beneath streetlights. They do not see color confinement or flux tubes or asymptotic freedom. And perhaps that is understandable. Human senses evolved for survival, not for perceiving quantum fields. Still, there is something quietly moving about the fact that beneath every familiar object lies a hidden storm of unimaginable complexity. A simple glass of water contains more confined quarks than there are stars in entire galaxies. Every atom inside that water carries internal gluon fields endlessly interacting at nearly the speed of light. The calm surface disguises violence occurring on scales too small for direct perception. Reality wears tranquility like a mask. This hidden turbulence becomes even stranger when viewed through time. The quarks inside your body are ancient beyond comprehension. Some were forged during the first minutes after the Big Bang. Others formed later inside stars through nuclear fusion. Heavy elements emerged during supernova explosions where collapsing stellar cores briefly reached conditions violent enough to reshape atomic matter itself. Those atoms drifted through interstellar clouds for millions or billions of years before eventually becoming part of planets, oceans, living organisms, and human bodies. And throughout all those transformations, confinement endured continuously. The quarks never escaped. Not during stellar collapse. Not during planetary formation. Not during biological evolution. For nearly 14 billion years, gluons maintained their invisible prison with absolute consistency. There is something strangely eternal about that. Human civilizations rise and vanish. Mountains erode. oceans shift, stars ignite and die, entire galaxies collide across cosmic time. Yet inside every proton, confinement persists almost unchanged. The smallest structures in reality can outlast worlds. Now imagine descending further inward still, beyond atoms, beyond nuclei, into the tiny realm where quarks race through gluon fields at almost light speed. At that scale, ordinary concepts begin dissolving completely. Position becomes uncertain. Particles blur into probabilities. Empty space seethes with virtual activity. Even the vacuum itself refuses stillness. Quantum theory reveals that what humans call empty space is actually alive with fluctuations. Virtual particles emerge briefly from the vacuum before annihilating again. Gluon fields ripple constantly through this quantum background. Reality never fully rests. The universe hums quietly beneath itself. And perhaps this endless motion is unavoidable. Perfect stillness may not truly exist anywhere. Even frozen matter contains atomic vibrations. Even black holes evaporate slowly through Hawking radiation. Even the vacuum fluctuates. Existence appears fundamentally dynamic. The gluon simply reveals that truth more clearly than most phenomena. There is another remarkable aspect of confinement worth lingering on for a moment. The prison created by gluons has no central authority. No external mechanism imposes the confinement from outside. The system confines itself automatically through its own internal rules. This self-organizing behavior appears throughout nature. Snowflakes form intricate structures without guidance. Galaxies spiral naturally under gravity. Biological life evolves complexity from simple chemical interactions. Consciousness itself may emerge from enormous networks of neurons following local physical laws. Order often arises spontaneously from interaction. The gluon demonstrates this beautifully. No external hand forces quarks into confinement. The mathematics of the gluon field naturally generates flux tubes whose energy increases with separation. The prison emerges automatically from the structure of the force itself. In that sense, confinement is not imposed. It is inevitable, and perhaps inevitability is one of the deepest themes running through physics. Given certain laws and certain symmetries, entire structures become unavoidable consequences. Stars become inevitable once gravity shapes hydrogen clouds. Chemistry becomes inevitable once stable atoms exist. Life may even become statistically inevitable once chemistry reaches sufficient complexity. The gluon participates in that chain of inevitability. Without it, the universe might remain simple forever. With it, complexity blooms. Matter stabilizes. Stars forge elements. Planets form oceans. Living minds emerge capable of wondering about the invisible fields holding reality together. And all because one force carrier behaves unlike every other. Particle carrying its own charge. A field interacting with itself. A prison woven from pure energy. The deeper one reflects on it, the more extraordinary ordinary existence begins to feel. Every breath becomes connected to confinement. Every heartbeat becomes connected to gluon fields, hidden inside ancient protons born near the dawn of time. The visible world begins feeling less accidental, less static, more like an intricate unfolding of invisible symmetries operating silently beneath perception. And somewhere inside those hidden symmetries, gluons continue their endless work without rest. When people imagine the future of physics, they often picture enormous machines searching for entirely new particles hidden beyond current theories. Dark matter candidates, extra dimensions, unknown forces waiting somewhere beyond the standard model. And those searches are indeed important. But there is another possibility that many physicists quietly consider even more profound. What if the deepest mysteries are not hidden beyond known physics? What if they are already sitting inside ordinary matter itself? The gluon hints strongly toward that possibility. After all, confinement remains only partially understood mathematically. The proton's internal structure continues revealing unexpected complexity at higher energies. Even the vacuum surrounding quarks behaves in ways that challenge intuition completely. The closer humanity studies the strong force, the more inexhaustible it seems. This is partly because quantum chromodynamics operates at the edge between simplicity and chaos. The fundamental equations appear compact, elegant even, yet their consequences explode into staggering complexity once gluon self-interaction enters the picture. A tiny adjustment in one region of the gluon field can ripple through the entire system. Every gluon affects others. Every interaction feeds back upon itself. The proton becomes less like a machine and more like weather. And perhaps that comparison is deeper than it first appears. Weather emerges from relatively simple physical laws governing pressure, temperature, and fluid dynamics. Yet from those laws arise hurricanes, lightning storms, atmospheric rivers, and chaotic climate systems impossible to predict perfectly over long timescales. The proton may behave similarly. Simple underlying laws generating turbulent emergent behavior. Some physicists even describe the gluon field inside protons using language borrowed from fluid dynamics. Under certain conditions, dense gluon systems appear to flow collectively almost like liquids. The quark-gluon plasma created in heavy ion collisions behaves less like a gas of particles and more like an ultra-hot, nearly frictionless fluid. Again, the old distinction between particles and continuous matter begins dissolving. Reality resists rigid categories. This pattern appears repeatedly throughout modern physics. Light behaves both as particle and wave. Electrons spread through probability fields until measured. Black holes blur the line between gravity, thermodynamics, and information theory. Gluons blur the line between force and matter itself. The deeper one looks, the more the universe resembles an interconnected process rather than isolated objects obeying simple mechanical rules. And yet, despite all this abstraction, the consequences remain deeply physical. The strong force determines the stability of stars. It determines which atomic nuclei survive long enough to support chemistry. It determines how supernovae forge heavy elements during stellar death. It even influences the balance of nuclear reactions powering the sun right now. Every second, hydrogen nuclei fuse deep inside the solar core through processes ultimately shaped by strong interaction physics. The sunlight drifting quietly across Earth today carries within it the hidden signature of gluon dynamics operating inside stellar plasma. There is something beautiful about that connection. The warmth on your skin traces backward through nuclear fusion into confinement and color charge hidden inside protons. The ordinary world remains tied intimately to invisible quantum fields. Now let us return briefly to the earliest universe, because gluons may have played an even more dramatic role shortly after the Big Bang than they do today. During the first tiny fraction of a second after cosmic expansion began, temperatures exceeded anything humans can truly imagine. Matter existed as an almost featureless fireball of elementary particles and radiation. Quarks and gluons moved through dense plasma without forming stable protons or neutrons yet. Confinement had not fully emerged. But as the universe expanded and cooled, a critical transition occurred. The quark-gluon plasma condensed. Quarks became trapped inside hadrons. Protons and neutrons stabilized for the first time. In some sense, this transition marked the birth of ordinary matter itself. Before confinement, the universe lacked atoms, chemistry, planets, or biology. After confinement emerged, complexity slowly became possible. The invisible prison created the material universe. That moment may have been among the most important phase transitions in cosmic history. Without it, the universe might never have progressed beyond an expanding sea of elementary particles. And yet, despite its importance, humanity still cannot recreate the full conditions of that era except briefly inside particle colliders. The Large Hadron Collider and similar experiments generate tiny droplets of quark-gluon plasma lasting only infinitesimal fractions of a second. Detectors capture the debris after the plasma cools and confinement reasserts itself. Physicists then reconstruct what happened indirectly through sophisticated models and enormous datasets. It is extraordinary when you think about it. Human beings evolved on a small rocky planet orbiting an ordinary star. And somehow those beings learned to recreate conditions resembling the first microseconds after the Big Bang itself. Not perfectly, not completely, but enough to glimpse the ancient behavior of matter before confinement shaped the universe we know. Few achievements reveal human curiosity more clearly than that. And perhaps curiosity itself deserves reflection here. Because the gluon is not a practical discovery for most people's daily lives. Understanding confinement will not help someone cook dinner or navigate traffic or fall asleep at night. Yet humanity pursued this knowledge anyway. Because somewhere deep inside human consciousness exists a desire not merely to survive, but to understand. People look upward at stars and inward at atoms for the same reason. They want to know what reality truly is beneath appearances. The gluon became part of that journey. A hidden force carrier discovered not through direct sight, but through patterns, mathematics, and persistence. A particle revealing that matter itself is stranger than ancient philosophers or modern intuition ever imagined. And tonight, even as you rest quietly beneath the dark sky, countless gluons continue moving silently inside every atom around you. Invisible, massless, forever confined, yet endlessly building the structure of the visible universe from imprisoned energy and hidden storms. There is a certain calmness that arrives when you realize the universe does not need human understanding in order to function perfectly. Long before the first living cell appeared on Earth, gluons were already binding quarks together inside ancient stars. Long before language existed, confinement shaped the structure of matter silently across the cosmos. The strong force worked in darkness for billions of years before any conscious mind finally uncovered a small part of its hidden logic. And even now, most of its activity remains forever beyond direct perception. Perhaps that is why the gluon feels almost mystical compared to other particles. Not mystical in the supernatural sense, but mystical in the sense that it reveals how incomplete ordinary intuition truly is. Human senses evolved to navigate forests and rivers, to recognize faces, to avoid predators. Nothing in human evolution prepared the brain to imagine self-interacting quantum fields generating mass through confined energy inside invisible flux tubes. And yet reality operates that way regardless. There is something humbling about this. The universe is under no obligation to resemble human expectation. At the same time, there is something deeply hopeful about the fact that human beings still manage to uncover these truths. Through mathematics, through experimentation, through patience stretched across generations of scientists slowly refining one another's discoveries. The gluon was not discovered in a single dramatic moment. It emerged gradually through decades of confusion, failed models, strange scattering data, and increasingly powerful theories. Physicists first struggled simply to explain why nuclei remain stable. Then came the particle zoo of the mid-20th century, where accelerators revealed hundreds of strange hadrons nobody fully understood. The growing chaos threatened to overwhelm particle physics completely. But hidden beneath that apparent complexity was a simpler structure waiting to be uncovered: quarks. And beneath the interactions of quarks waited something stranger still: gluons, the force carriers that trap themselves. There is a pattern here repeated often throughout science. Complexity on the surface hiding deeper simplicity underneath. The night sky once looked chaotic until gravity explained planetary motion. Chemical reactions seemed mysterious until atomic theory emerged. Electricity and magnetism appeared separate until Maxwell united them into electromagnetism. Again and again, hidden symmetries reveal order beneath confusion. Quantum chromodynamics became another step in that ancient journey toward hidden structure. And yet, unlike some earlier theories, QCD did not simplify reality into comfortable mechanics. Instead, it exposed deeper layers of turbulence and abstraction. Fields replaced particles as the primary language of nature. Probabilities replaced certainties. Confinement replaced separability. The universe became less like a clockwork machine and more like a dynamic ocean of interacting processes. Perhaps this shift explains why quantum physics feels emotionally different from older science. Classical physics often reinforces human intuition. Objects move through space according to predictable laws. Causes produce effects cleanly. But quantum fields refuse such simplicity. They overlap, fluctuate, interfere, blur the distinction between emptiness and activity. The gluon sits directly inside that strange territory. Invisible yet essential. Massless yet responsible for mass. Confined yet generating the visible universe. And perhaps the strangest aspect of all is that gluons may never truly rest. Inside every proton, gluon fields remain active continuously. Even in matter sitting motionless on a quiet table, the internal quantum world churns endlessly. Quarks race through confined regions at relativistic speeds. Gluons emerge and vanish constantly. Virtual particles ripple through the vacuum. Stillness becomes an illusion produced by averaging over enormous microscopic motion. This idea echoes beautifully across larger scales too. A calm ocean from orbit hides powerful currents beneath its surface. A peaceful forest contains endless biological activity. Even galaxies drifting slowly through darkness contain billions of stars orbiting at tremendous speeds. Nature often hides motion beneath apparent stability. The proton may simply be one more example. Now imagine all the protons inside your body simultaneously. Every atom in your cells contains nuclei stabilized by confinement. Every nucleus contains protons and neutrons. Every proton contains quarks immersed inside gluon storms. The scale becomes difficult to emotionally process. There are more protons inside your body than stars in the observable universe. And inside every one of those protons, confinement has operated continuously since near the beginning of cosmic time. The same invisible force binding ancient stars together now quietly stabilizes your heartbeat. There is something profoundly intimate about that connection between the cosmic and the microscopic. Humans often feel separated from the universe as though consciousness exists apart from the physical world observing it from outside. But gluons remind us that life emerges entirely from the same fields governing stars and galaxies. Your body is not separate from cosmic history. It is one expression of cosmic history. The calcium in your bones formed inside stars. The hydrogen in your blood dates back to the early universe. The confinement structures inside your atoms were forged during the first moments after the Big Bang. You are built from ancient imprisoned light. And perhaps that phrase is not merely poetic, because mass itself emerges largely from confined energy. The visible world is energy shaped into stable patterns by gluon dynamics and quantum fields. Matter is frozen motion. Structure is balanced turbulence. Existence is organized energy sustained through invisible interactions beyond direct perception. The deeper physics descends, the less the universe resembles dead machinery, and the more it resembles an unfolding symphony of relationships between fields, forces, and probabilities. And hidden deep within that symphony, gluons continue their endless silent work, binding quarks together, sustaining atomic nuclei, holding the visible universe in place one confined storm at a time beneath the dark and ancient sky. And now, as the night grows quieter around you, it is worth pausing for a final moment beside this strange invisible particle that almost nobody thinks about, yet which quietly shapes the existence of everything familiar. The gluon does not shine like a star. It does not curve space-time dramatically like a black hole. It leaves no visible trail across the sky. And yet, without it, there would be no stars to shine at all. No planets, no oceans, no living creatures capable of gazing upward into darkness and wondering what reality truly is. The gluon hides beneath all of it, hidden beneath mountains, hidden beneath oceans, hidden beneath the atoms inside your hands resting quietly tonight. There is something strangely peaceful about realizing how deeply connected everything becomes at the smallest scales. The atoms inside your body are not isolated from the rest of the cosmos. They participate in the same ancient physical laws shaping galaxies billions of light years away. The confinement structures inside your cells obey the same quantum chromodynamics operating inside distant stars and neutron star collisions. The universe does not separate itself into human categories, large and small, living and non-living, cosmic and personal. At the deepest level, all of it flows together through shared fields and interactions. And perhaps that is part of why studying physics can feel unexpectedly emotional sometimes. Not because equations themselves contain emotion, but because they reveal continuity. They show that existence is woven together far more intimately than daily experience suggests. The gluon becomes one thread inside that immense cosmic fabric. A thread carrying invisible tension through all visible matter. And what an extraordinary thread it is. A massless particle generating mass. A force carrier imprisoning itself. A hidden field creating the structure of atoms while remaining forever trapped inside them. Reality did not need to behave this way. The laws of physics could easily have been different. The strong force might have weakened with distance like electromagnetism. Quarks might have drifted freely through space. Stable nuclei might never have formed. Chemistry might never have emerged. But the universe chose another path. A path where confinement became possible. A path where invisible storms stabilized into matter. A path where stars eventually forged the elements necessary for oceans, forests, music, memory, and consciousness. And somewhere inside all those possibilities, gluons quietly continued their endless work. Even now, while civilizations sleep beneath the night sky, gluon fields remain active inside every atom on Earth. They churn invisibly beneath mountains and deserts, beneath sleeping cities, beneath waves rolling slowly across dark oceans. The visible calmness of the world rests upon microscopic turbulence too small for human senses to detect. Reality hums softly beneath itself. Perhaps that is one of the final lessons hidden inside quantum physics. The universe is not truly made from static things. It is made from relationships, interactions, exchanges of energy across invisible fields. Stability itself becomes a dynamic achievement maintained continuously through balance and motion. The proton survives because quarks move. Mass exists because energy remains confined. Matter persists because gluons never stop interacting. The universe sustains itself through endless activity, hidden beneath apparent stillness. And maybe there is comfort in that idea too. Human life often feels fragile because everything visible changes eventually. Stars die, species vanish, civilizations fade into history, even galaxies evolve slowly across cosmic time. Impermanence seems woven into existence everywhere we look. Yet beneath all those changing forms, the deeper structures of reality endure with astonishing consistency. The same gluon dynamics operating inside your body tonight once operated inside the first stars forming after the cosmic dark ages. The same confinement principles shaping modern atoms existed long before Earth formed, long before life appeared, long before human beings first looked upward and wondered about the sky. There is continuity beneath change. Ancient, invisible laws quietly holding reality together across billions of years. And perhaps that is why the study of particles can ultimately feel less cold than people expect. Beneath the mathematics lies a strange kind of intimacy, a realization that human beings are not strangers standing outside the universe examining it from afar. We are expressions of the same forces we study. The atoms inside your body emerged from cosmic history itself. The gluons inside those atoms belong to structures older than Earth, older than the sun, older than life. You are built from ancient confinement, built from imprisoned energy stabilized into temporary form beneath an ancient sky. And one day, far in the future, the atoms composing your body will scatter again into the wider cosmos. Some may drift into oceans, some into distant soil, some perhaps into future stars not yet born. But even then, confinement will remain. Gluons will continue binding quarks together silently as the universe evolves onward through ages beyond imagination. The invisible prison will endure. The hidden storms will continue. And somewhere across the darkness, stars will still burn because massless particles refuse to behave normally near the beginning of time. So tonight, as you rest beneath the quiet sky, remember this strange truth hidden beneath ordinary matter. Inside every atom around you exists an invisible storm. Inside that storm live particles that can never escape. And from their eternal confinement emerged the entire visible universe.